Well, for probably our final topic of the semester, we're going to talk about numerical methods for solving a differential equation. Numerical methods don't actually solve them, but they estimate them very closely. Remember, I put that in quotes, most differential equations probably can't be solved symbolically the way we would like to do it. So we have to resort to numerical methods to come up with an excellent approximation. So that's exactly what Euler's method is going to do. Numerically solving, I should have maybe said estimating or approximating a differential equation, and just at certain points. So what we're given is the differential equation. Actually, an initial value problem is what it needs to be. We're given this, which is essentially a slope field. We can tell the slope of the solution at any point in the plane. Remember those line charts that we made, line graphs? And then this is the key point. This is the only ordered pair of the solution that we know. So what we're going to do, let's say that this is the solution, but we don't know it. But let's say that's the true solution. Here's how we will estimate y at a point different from x naught. So maybe I should write that down, the goal. Estimate or approximate. I'm going to put determine, and maybe I'll put approximately in parentheses. Determine y at any value of x. That's what we're going to try to do. Again, the only one we know exactly is this. And I drew a graph, and so let's say that we know that position. That's actually on the solution, the function. The y equals f of xy. Not this f of xy. This is the slope at any given point. So for example, we know x0, y0. And let's just say it's here. I made x0 look like it's equal to 0, and that's fine. We know the slope at this point. It's the tangent to this curve, but we're given that. We can just take that known value, plug it in here, and we get the slope. So what we're going to do is extend that slope until we get to the second time step. Maybe I should have called this t0, t1, t2, but I'm just going to treat the x-axis as time. So at time x0 or time 0, we know it, and so we're going to just do a linear extrapolation. Keep the slope and stop when you get to x1. So this point right here is our estimate of x1, y1. Again, it's an estimate. So now what are we going to do? Well, it's an estimate, but we know the exact slope of the slope field that this defines at this point. All we have to do is take our x1, y1 and plug it in here and get the slope at this point. We really would wish we had the slope at this point, the true value at x1, but hopefully if it's close in proximity, the slopes would also be close. So if we plug that in, then let's say we get something like this. This would then be our estimate of x2, y2. And the x values are not estimates at all. I mean, we know x1, x2, x0, x1, x2. It's the y's that we're estimating. Because after all, the solution is going to be y equals some function of x and y. So, in this graph, it looks like we're a good distance away. But let's notice there that Maybe I need to move my x2 over a little bit. Let's call that angle theta in that triangle. We know that the tangent of the angle theta is a right angle. So what's tangent? Opposite over adjacent? Well, what is this width right here? It's y2 minus y1. And this is x2 minus x1. And that happens to be equal to the slope of segment or line connecting x1, y1 and x2, y2. And we actually know what that is. That's f of x1, y1. We didn't even have to compute this. We could have gone straight to f of x, y to get that. Now, yeah, the only problem is at this step is x1 we know all of the time steps, and by the way, we're going to use equal length time steps. So this is the same as this. y1 is our estimate, because we just did a straight line approximation to get us to this point. All right, well, let's see if I can get the equation of Euler's formula before the video ends. I'm going to use red. In general, what we have is f of xi, yi is equal to this thing right here, but I'll say it as yi plus 1 minus yi over xi plus 1 minus xi. That's really our estimate. We're using the slope of that line segment. So if we solve for this, the only unknown there is really yi plus 1. So I'm going to say yi plus 1 is equal to yi plus f of xi, yi. All I'm doing is solving this equation for yi plus 1. I'm multiplying both sides by this. And that's what we get. This is what we would call the step size. And it's going to be the same no matter what value of I is. The distance between x1 and 2 is the same as the distance between x2 and 3, or 3 and 4, and so on. So Euler's formula, I'm going to squeeze it in here, and maybe I'll choose to go back to blue, Euler's method. It's essentially what I have written up here with one little minor modification. I plus 1 is yi plus, instead of using this, I'm just going to use h, because the step size is the same all the time. So I'm going to say f of xi, yi, h. And I'll write down that h is equal to xi plus 1 minus xi. That's a constant. I'll put fixed width. So using this formula, you could estimate the value of y at any value of x. So let's say, for example, that we knew x naught, y naught, because we were given the initial value, and we wanted to know x2. But we were going to do it in 3 steps instead of 2. All we would do is we would do x0, x1, x2, x3, evenly space them, And we would have to do this one extra time. And in general, the shorter the time steps are, the more accurate your result is going to be. And we'll do some examples in the next video.